So next up, the pressure stabilized Petrov-Galerkin method, PSPG. We saw in our matrix system of equation here that involves the pressure test functions, and it's going to show up in the lower half of our matrix. So I've tried to motivate these stabilized methods from various perspectives, from the perspective of coercivity, that's a mathematical interpretation, from the perspective of discretization, the sensitivity with respect to the mesh size, from the perspective of the physics, right, that we have an artificial diffusion hidden inside of the stabilized method. So let me also try to motivate this from the perspective of the physics. In this case, it's not going to relate to any form of artificial diffusion, but rather it's going to relate to a sort of a relaxation of our incompressibility constraint. Our incompressibility constraint is a physical constraint. We don't want our fluid to compress. But that's a pretty harsh constraint, especially from the perspective of a discrete method. So we try to relax that a little bit, and we'll try to relax that consistently. So we're going to do a consistent relaxation of our incompressibility constraint. And the consistency is very important there. And again, that has to do with the residual-based nature of this equation, of this stabilized method. So our incompressibility constraint was that the divergence of UH was equal to 0. So now we're going to relax that a little bit. We're going to say not necessarily the divergence of UH has to be 0, but we're going to have minus some parameter tau times the residual of the momentum equation. Yeah, so if U cannot be exactly divergence free, then we won't force this in some sense, but we try to balance this with the momentum residual. So if we then use this strong form equation as the basis of a weak form equation, we obtain a weak form by multiplying by a test function. This is a scalar equation, so a scalar test function and integrating over a domain. And pretty much that's already the end of the story, because what we obtain is an integral over our domain omega of the divergence of... This is a linear operator, so it simply separates. Get the divergence of U times our test function Q minus how do I want to write this? I'll write this as a sum over elements. Minus the sum over the elements of the integral over the elements of the divergence of tau Rm times Q. And then the way that we typically make use of this is we don't like to have any additional derivatives on our residuals, so we do integration by parts. And now this is where the physical interpretation doesn't 100% fit. If you would do integration by parts, you would actually also get boundary integrals. And so now we assume that the momentum residual, which is vector valued, maybe a bit consistent there, yeah, is equal to 0 on the, or maybe even more specifically, Rm dot n. Times the normal vector is equal to 0 on the boundary of each element, so then that becomes the same thing as divergence of UH times Q minus the sum over the elements of the integration over the elements of tau times the residual times m times the gradient of Q. Okay, and that's pretty much already it. We now see that we have the residual of m, which is a function of both u and p. that is weighted against a test function on Q, and that's precisely what we require to fill this lower part of the matrix. And again, let me stress, this is a residual-based stabilization method. It is of the order of a stabilization parameter multiplied by a residual, multiplied by a differential operator acting on a test function. Now let me then conclude also by incorporating SUPG. This is the one that we already drew out here at the top, so I'm not going to repeat that. But this is a direct extension of the SUPG stabilization method of the advection diffusion equation, where we have a momentum residual multiplied by a stabilization parameter and multiplied by the advective part of the operator of the momentum residual. And in this case, we're no longer dealing with scalars, we have vectors, and so you get a gradient of a vector that gives a second order tensor, so we have to dot that with our advective vector. But other than that, it's the same principle. Yeah? And because the residual incorporates U and P, that fills the complete upper part of our matrix. Okay, so I think that's it. Now we have all our expressions for all our stabilized methods. We understand where they come from. We understand how they fill our matrix. And the next part of the story is going to be trying to figure out if we use all these stabilized methods, can we choose our test or our stabilization parameters tau in such a way that we retrieve coercivity of our Stokes, of our O'Shean equation, of this discrete set of equations. Yeah, so that's going to be the next video. Thank you for your attention.